Now we need to introduce the probably most important topic that's going to take us through the rest of the semester, and that is functions of several variables, multivariable functions. Oftentimes calculus is called calculus 3, I should say, is called multivariable calculus. And so this is it. This is where we finally start getting into the major parts of Calc 3. All right, so you've dealt with single variable functions since, I don't know, maybe middle school and high school algebra, essentially, right? So the idea here is you have a single variable function, you have a single independent variable, and a single dependent variable. And so you had this model of what a function looks like, where you have a domain, you have a range. Oftentimes the domain was X and the range was Y, but these are just arbitrary variables, so they could be anything. And the idea is for every element in the domain, it gets matched up with exactly one element in the range, okay? And so you plug a real number in. This was often some set or subset of the real numbers, and you would get some set or subset of the real numbers out. So a real number in, a real number out. Okay, so something like 2 would get matched up to, I don't know, 7 based off of some random function. Okay, this was the concept of a single variable function, and often y was your f of x. Okay, so this was this function that did this. All right, but that's a single variable situation. And that's what you've dealt with up to this point through algebra, through pre-calculus, Calc 1, Calc 2. You've done integrals, you've done derivatives, you've done limits, all with these single variable functions. Now what we want to do is you want to get into the concept of a multivariable function. Okay? And for a multivariable function, the concept is that the domain is no longer just a single variable, but there are multiple variables in this domain here. Okay? So not just x, but possibly x and y, in which case you see that here. This would be a two independent variable function. Now the range consistently will say a single variable, say f of xy or z. If we have a three independent variables, okay, that's in your domain. But the range is still a single variable, say w or f of xyz. And though this is very common in the real world, that you would have multiple independent variables acting together to create a single dependent variable. And we think about a simple equation like this. Work equals force times distance. Work is dependent on both force and distance. Okay? And so you don't just have one independent variable, but multiple independent variables. And so this is what we need to get used to studying here. And the more you remember and understand this concept of a single independent variable, the better we'll be able to understand and work with these multiple independent variables. So we start with two variables, okay? So let D be the set of ordered pairs of real numbers. If to each ordered pair xy in D there corresponds a unique real number f of xy, then f is called a function of both x and y. The set of x and y's is the domain, and the set of f of xy's is your range. Okay? So in this case, x and y are your independent variables, and f of xy, or we can label that as z, is your dependent variable. These are completely arbitrary letters here. It doesn't have to be x, y, and z, but this is what we would typically see. And so if we were to draw this picture similar to what I just did with the single variable, here's your domain, here's your range. The domain now consists of points x, y, okay? Ordered pairs x and y. There's not just a single variable, but there's two variables there. And this function f will then map those to a single variable, say f of xy or z, in the range. In which case we could say something like the point 1, 2 is mapped to 5, something like that. This is the concept of a multivariable function. Well, look at the domain. The domain is a set of ordered pairs. The domain is a set of points in the xy plane. So what we're doing is we're mapping R2, a set of points in the xy plane, not just a single real number, but an ordered pair of 2 real numbers. And that's getting mapped to a single real number. So think of it as 2 dimensions, say x and y, getting mapped onto a single real number line. Okay? Take a point here, match it onto a real number line. Take a point here, match it onto another point on the real number line, etc. Okay? And so this is the concept of a multivariable function, in this case a 2-variable function, right? To evaluate it, you just plug it in. I mean, if you think of a multivariable function, say f of xy equals 3x squared plus 2y squared plus 1. If I was to say find f of 3, 7, that's my ordered pair I'm plugging in. That means I'm going to plug 3 in for x, 7 in for y. So I get 3 times 9 plus 2 times 49 plus 1. And very simply, I would get 27 plus, what's that going to be, 98 plus 1. So 27 plus 99 would give me 126. This should be very easy. I mean, I'm not spending a ton of time doing this. This is real basic stuff you could have done way back in algebra pre-calculus as you learned about multivariable functions possibly back then. You didn't. You mainly stuck to single variable functions, but you very well could have. It's not that complicated of a step. It's just changing the domain, okay? So one of the first things you do with functions is you start to try to identify what the domain and the range of a given function is, so that you know what values you can plug into that function and then what kind of values will come out. And the domain oftentimes is a little bit easier to find than the range is. Knowing what you can and cannot plug into a function is what we're talking about here with the domain. And so when we look at, say, this multivariable function, we got to figure out what ordered pairs x and y's will we be able to plug into this function so that that ordered pair x and y will get mapped to something. Because the definition of a function is that each element in the domain gets mapped to exactly one element in the range. Okay? Each, so you only can pick the values for your domain that get mapped somewhere. Okay? If it doesn't get matched to another value, it cannot be in the domain. So to do that, we're going to use a lot of the same techniques we've used back with single variables. First off, we know that this is a square root, and the domain for square roots is that this value inside the square root here has to be positive or 0. It cannot be negative unless we want to travel to the imaginary set, but we're doing real calculus, so we're not doing that. So what I'll do here is I'll look at the square root of 16 minus x squared, and I'll factor out a negative, so I get x squared plus y squared. So the general idea here is for this to be greater than or equal to 0. I'll just set it greater than or equal to 0. In which case, if I move this to the other side, I get 16 is greater than or equal to x squared plus y squared. So these are the x's and y's that I would like to use so that this thing becomes in my domain. Right? So I can identify my domain. All right, so we need to identify these ordered pairs. And how are we going to, well, if I gave you the equation 16 equals x squared plus y squared, and I said, tell me what ordered pairs satisfy that equation, everyone should recognize that as a circle centered at the origin, radius 4. So if I was to draw all the ordered pairs that satisfy that equation, it would be these ordered pairs that sit on this circle. Okay? But I don't have the 16 equals only. I have 16 equals x squared plus y squared, or 16 is greater than x squared plus y squared. Or you could say x squared plus y squared is less than 16. So I need to figure out all the ordered pairs that would satisfy the x squared plus y squared is not just equal to 16, but less than 16. Well, to throw that into this picture, it would basically be all the points on the inside of the circle would be all the points that would be able to satisfy this inequality. And so if I was to draw my domain, it would be all the points that sit inside this circle. That's my domain. So how would I write this down? Well, I would write this down in this way. I would say that the domain is the set of all x's and y's such that x squared plus y squared is less than or equal to 16. Now, that's the official way to write it down, but does that really tell you a whole lot? I don't know. I think the visualization here gives you a better idea of what ordered pairs you will be able to plug into this function. All these points that sit inside here, when I plug them into this function, I'll be able to get a z value or an f of xy out. Okay, so there's my domain. Now the big question is, what about the range? What's the range for this function? Once I plug all these points in, okay, what kind of answers am I going to get to come out? What's this going to be? So there's my domain. That's the domain there. What's the range going to be? Well, start to think about it. If I was to say, let's plug in 0, 0, that's in this side of the circle. These two would be 0 and 0. And I would get the square root of 16, which would give me 4. Okay? So that's one value in my range. Okay, so the idea here is that 0, 0 gets matched to 4. All right. Let's start looking at what's happening as we move away from that origin. Well, as I start moving away from that origin, let's say I start moving along the x-axis this way, or I move diagonally, or any one of these directions, but let's just go along the x-axis this way. I'm going to start plugging in x and y values, and what's going to happen is the x is going to get bigger, but the y is going to stay 0. So this is going to keep getting bigger and bigger, but not infinitely bigger. It's only going to max out at 4. And this is going to stay 0. But what's going to happen to this whole piece here? Well, remember, it's the same thing as this. So this piece is going to start getting bigger, okay? And I'm going to be subtracting it from 16. So this whole thing inside the square root is going to start getting smaller, till eventually this is going to turn into 4 squared plus 0, which is going to be 16, which is going to make this whole thing 0. So as I move this way, the range values are going to get closer and closer to 0. That's the same thing that's going to happen as I move this way, or this way outward from this origin. I'm going to max out at 0 because I'm going to max out at the outside of the circle. And any point on the outside of this circle is going to make x squared plus y squared equal to 16, and I would have 16 minus 16, therefore making the whole function value 0. So if I was going to write the range down for this, I could say the range is a set of all f of xy, or I could even say z, such that f of xy is between 0 and 4. And there's your domain, and there's your range. Here's another function. It's a logarithm. So you have to have a general understanding of how domains and logarithms work. This right here has to be greater than 0. Okay? You cannot take the log of 0, and you cannot take the log of a negative. So whatever x and y are, this has to be greater than 0. So we start there. So x minus y squared has to be greater than 0. That's the same thing as saying x is greater than y squared. And so I could say, all right, well, then the domain is the set of all x's and y's such that x is greater than y squared. And while that does define the domain for this function, that doesn't really give you a great idea of where the ordered pairs that are in the domain actually sit. So I like to graph the domain, so I really get an idea of what points I can use into this function. And so I look and I say, okay, I got to graph this inequality. X is greater than y squared. Well, if x equaled y squared, it would be a parabola this way. But x doesn't equal y squared. X is truly greater than y squared. So what I'm going to do here is I'm going to use a dotted line for that parabola, because all the points that sit on that parabola are actually not going to satisfy this domain, because I don't want x to equal y squared, but I want x to be greater than y squared. So I got to figure out what points actually satisfy that. Well, it's either the points on the inside of the parabola, or it's the points on the outside of the parabola. So the question is, which one is it? Well, the easiest way to find that out is to pick a random point on one of the sides. So I'll pick a random point here. Let's pick this point, let's say 5, 0. Does 5, 0 satisfy this inequality? If x was 5 and y was 0, would be 5 greater than 0 squared? Yes. So if that satisfies the inequality, then that means every point on the inside of this parabola satisfies the inequality, and therefore that's where my domain sits, right? That's a visualization of the points that satisfy this. And so there's my domain. All right, how about the range? All right, well, think about it. If I'm going to plug these points in here, think about the range of just a logarithm itself, right? A logarithm itself can go anywhere from negative infinity to positive infinity with its range. Can we still get that with these points? Well, the closer this in here gets to 0, the further to negative infinity we go with the range. Well, can I make this get very close to 0? Sure, I can. Okay, I could basically just move along the x-axis and make that happen. The y is always 0 as I move along this x-axis, and then the x is going to get closer and closer to 0 as well, therefore making this get close to 0 and the logarithm itself get closer and closer to negative infinity. Now, as far as logarithms go, if this piece inside the logarithm gets larger and further away from 0, then the logarithm itself goes to positive infinity. Well, I can do that by moving this way along the x-axis. So just traveling along the x-axis, let alone all these other directions, in this domain, will allow me to get the range of values to be the set of f of xy's, such that, f of xy goes between negative infinity and positive infinity. So if I was to say, all right, well, here is my range, this function maps this set onto this set. That's what this function g does. All right, and I should really actually say g, the set of g of xy's. Well, because that's the name of the function here, right? It's a g function, not an f function. But that's what this function does. It takes all these ordered pair points in here and matches each one onto a particular real number on the number line between negative infinity and positive infinity. Okay? So now that you have an idea of how to work with the domain and range of a function, the next thing we want to start talking about is graphing functions. Okay? And again, just two variable functions. Okay? So the idea is an x and y is going to get mapped to an f of xy, or let's call that a z, okay? A single real number. And if we match them up, what we get is an ordered triple, x, y, and z. And so all the points x, y, z that satisfy the function such that x, y is in the domain and z is the range value associated with that will make up the graph of the function. So that's exactly what we say here. The graph of a function of two variables, two independent variables, let's say, is the set of all points x and y for which z equals fy, where x and y is in the domain of f. These graphs are basically going to be represented by surfaces in 3D space. Okay, so we talked about what the graph of a vector valued function looks like in the previous chapter, and those vector value functions were tracing out curves in 2D or even 3D space though, but the big idea was the 3D space. And so what do these functions of two independent variables graphically represent in 3D space? Well, they're going to represent surfaces. Okay? So the best way to realize this is this mapping method. and to think of your domain as a set of points in the xy plane, right? So here, this domain is this rectangle in the xy plane, square, rectangle, quadrilateral, okay, whatever. So this square down here represents the domain for a given function. And each one of those x's and y's is matched up with a z. And so if I take this x and y and match it up with its particular z, I then get this point. And if I take this x and y and match it up with its particular z, I get this point. And this one matches up and gives me this point. And this one matches up and gives me this point. And what I'm basically doing is I'm projecting this domain into the z direction, either upward or downward, to create this surface that is the collection of all x, y's, and z's that would satisfy the function. And that's the general idea of graphing a two-variable function and why it would represent the surface. So you see, like, this point here, if I erase some of this point here, its z value is 0, so it stays right where it is. But if I move a little bit further over, the z value is raised a little bit more, and the z value is raised a little bit more, and so on. So all these points kind of project upward based off of their corresponding z value. If their z value is negative, maybe some of them would project downward and the z value would be down here, and you would get a surface that might do something like this, where some z's project up, some z's would project down, and it would create this surface that would have its peaks and its valleys in it. So if we look at this example where we want to find the domain range and then also describe the shape of this function graphically, we could do so. Now this looks a lot like the previous example we did. The only difference I changed is 16 to a 25. So we start to look at that and say the domain, similar to what we did before, is we'd say the domain is the set of all x, y's such that x squared plus y squared is less than or equal to 25. Again, this is the same concept as the one we did before, except for this is 25 instead of a 16. We saw that that was essentially a circle radius, now the 5 instead of 4, so 5, and all the points that lie on the interior of that, okay, including the points along the rim because of the or equal to. So that's our domain. The range, similar to the example we did before, is all the z's or f of x, y's, let's just say z's, such that z is going to be between 0 and, in this case, 5. Okay? It was 0 to 4 before, but now it's going to be 0 to 5, because again, think about what's going to happen here. These, as x and y go from 0 all the way out to 5 in any direction, okay, this is going to max out at 25, which is going to be the square root of 25, which will be 5. But then as x and y start getting bigger, this is going to start to shrink down to 0. And so those are our z's. So then this is going to be mapped on to the real number line, but only between 0 and 5. So this is essentially the mapping we're dealing with here. Okay? Now graphically, what's that going to do? Well, let's think about that. If I was to look at this in the xy plane, okay, and my domain is this circle here, and we said that this point right here, 0, 0, gets matched up with a z value of 5, that would be here, so we get the point 0, 0, 5. And as I move outward along this circle in my domain, the z values will start becoming smaller. And so to the point where I get to the outside of here, the z values on all these points on the outside, like say this point or this point, which would be say 5, 0 or 0, 5, would have a z value attached to it of 0. Because if I plug them in the function, that's what's going to happen. And so what you end up getting is a surface that looks like this. And what you have is the upper hemisphere of a sphere, okay? Which shouldn't be that unusual for you to look at, because if I replace the f of xy with a z, and I have the square root of 25 minus x squared minus y squared, and I square both sides, I get z squared equals 25 minus x squared minus y squared. And then I add the x and y squared to the other side, I get x squared plus y squared plus z squared equals 25. And that you should recognize as a sphere radius 5. Now that's the full sphere. We only have the top half because we only have the positive square root here. There's a positive and there's a negative square root. We only have the positive, so it's the upper hemisphere of a sphere radius 5. So graphically, that's the shape we would be describing here with this function, by recognizing this domain getting matched onto this particular range.
One of the biggest issues we have when we are trying to graph one of these surfaces is something we've discussed multiple times already this semester, is trying to do it on a two-dimensional space, as in the whiteboard or on a piece of paper or this computer screen. And because you're trying to depict a 3D image in two-dimensional space. So there are issues that arise in that. And so, with computer modeling and shading, we can make it appear as if we're sitting in 3D space on the screen, even though again, we're doing it on a flat surface. So one way to do this and to kind of get around this issue is with something called level curves. And the idea here is to flatten essentially the 3D image down into a two-dimensional space. So, you think of the z value as essentially a constant, in which case, we shrink everything down so that the z coordinate turns into a constant value, and we look at what we call a scalar field, f of x equals c, or c some real number assigned to that point xy. And so this right here would be a picture of that level surface, where you only are looking at the domain values, and certain domain values are assigned a constant, which would be its associated z coordinate. And each one that has a similar z coordinate, let's say everything along this ring here, the z coordinates for all the domain values on this ring have a z coordinate of 7. And so we'll draw a curve that essentially groups all those points together as having the same z value of 7. And then I can do it for another group of values in my domain, and looking at the z value associated with those, and as those all have a z value of 6, and I'll put a curve around those, and I keep doing this. And what happens here is that you see that each one of these values is representing us moving either upward or downward in the z direction, depending on whether or not the associated constant or the associated z value is positive or negative. And it will give you an idea of how this image would look in the z-axis, as if the z-axis were coming out of the screen at you. So you have the x and y for your domain, okay? And you will plot the domain values, and each domain value, its associated z value, is what we're going to call a level, or a level curve, in this space. And so this picture right here, I think, really does justice to this idea. Whereas if I had a surface, which is this wire mesh, is the surface that we'd be talking about, and you see we have a peak here, we have a valley here. And the idea is, if I looked at this from above, from this side, and I said, okay, well, this right here represents a z value of 0. Everything around the edge is a z value of 0. And as I start moving up this surface here, each one of these different levels I reach, which would have a z value of, say, I don't know, 1 or 2 or 3 or 4, or in this case it looks like 0.1, 0.2, 0.3, 0.4, I'm going to assign a curve for that level that I'm going to project down here in this flat space. And I'm going to say, okay, here's the 0.2 curve, here's the 0.3 curve, here's the 0.4 curve. And in this case, where we have sort of the valley, the opposite's going to happen. I'm going to create these different levels here at certain spots, and they're going to be represented by negative. So negative 0.1, negative 0.2, negative 0.3, etc. And then when I look at it in this flat space, what I'm going to get is something that looks like this. And if I label it as, 1, 2, 3, point 1, point 2, point 3, whatever, and -1, -2, -3, etc., what I can do is I can look at this series of level curves and realize, well, what do I have? What I have here is I have a mountain here that's going to be rising up to this point, and I'm going to have a valley here that's going to be decreasing down to this sort of low spot. And I can see sort of a 3D image really just by looking at this flat two-dimensional figure. And so the level curves help you do this. And this is really how a topographical map would be drawn. And I think we've all seen stuff like that before. So this level curve surface is a great way to depict a 3D image, but still keeping it in 2 dimensions and avoiding some of the issues that we get in trying to do so, say like this. Drawing this freehand would be kind of difficult, but computer images allow us to do this in a much easier fashion. So we've discussed 2 independent variable functions, but what about 3 independent variable functions or 4 independent variable functions? Well, it's just increasing the number of independent variables. So let's say we talk about 3 independent variables. Typically we would use x and y and z as our independent. And it's just a rule that assigns each ordered triple now in our domain to exactly one real number in our range. And let's say that real number is w, right? W is typically the dependent variable we use with a 3 independent variable function. And so we kind of use that same mapping principle of, okay, here's our domain, here's our range. We're going to get this mapping from here to here with this random function, but our domains now is going to be this ordered triple, and our range is still going to be this single real value, single real number, say w, which is going to be f of x, y, z. And as far as the mapping goes, this is an ordered triple, so this is a set of points in 3D space being mapped to a single real number, in which case you kind of think of the domain as a bunch of 3D points in 3D space, and all these points here are going to get mapped onto, again, still just a real number line. Okay? So this point gets mapped onto this real number, this point gets mapped onto this real number, etc. And so it's really just an extension of what we've seen with the 2 independent variable functions. Now, here's the tricky part. When we take a 2 independent variable function and we look at it graphically, we get a 3-dimensional figure. And we said it was a surface. Why? Because we have the x and the y is our independent. What it gets matched up to is the z creates our 3-dimensional point, and the collection of those points creates the graph of the 2 independent variable function. So now we have 3 independent variables. That gets matched up with a fourth value, which is the dependent variable. And now we have a 4-component ordered point. And so graphically, this would be something in 4-dimensional space. And you might say, well, what does 4-dimensional space look like? Well, that's the trick, okay? It's not very easy for us to see what a 4-dimensional object would look like because we live in a 3-dimensional world. If any of you have ever read the book Flatland, it's about, a world of people or beings that live in 2-dimensional space and then become aware that there's this other 3-dimensional world that they can't see. Einstein kind of took this idea with his theory of general relativity about sort of light bending around large mass objects, and this idea of space-time as the 4th dimension. So, but nonetheless, it's a pretty difficult thing for us to visualize because we live in a 3-dimensional world. Think about the whole idea of how we have a hard time drawing three-dimensional figures in a two-dimensional surface like a chalkboard. Well, we have an even harder time visualizing a four-dimensional concept because we live in a three-dimensional world. The best way we can do it is to do it using what we call level surfaces. So think about how we do things with level curves. Okay? In level curves, you take a three-dimensional object. In that three-dimensional object, you flatten it down to a series of two-dimensional curves to describe that three-dimensional object. So when I give you a figure like this, and I say, here's a curve, here's a curve, here's a curve, and I said 1, 2, 3 as the labels for those levels, right away everyone should be seeing this as a mountain or a hill, okay? Where I'm going to be slowly walking up the hill and going up from level 1 to level 2 to level 3. But this is a two-dimensional drawing. But you are, in a way, visualizing a three-dimensional surface. Well, we try and do that same thing for four-dimensional figures. And so we flatten it down, I use that word loosely, to three-dimensional space through a series of surfaces, where each surface represents a different level in four-dimensional space. So if we were to say graph this figure right here, I can't show you what that figure looks like in four-dimensional space because I would be constantly be representing it in a 3D world. And so it's even harder because I'm actually representing it in a 2D world because this screen that I'm working on right now is a flat 2D screen. So what we're going to do, though, is represent it in these level surfaces. So each one of these surfaces that you see here, this surface in here, this surface in here, this surface in here, they're all wrapped around one another. They represent how I would be moving through four-dimensional space. In which case I would go, say, if I labeled them, I don't know, 1, then 2, then 3, and I can't even see that. So let's say, 1, then 2, then 3, then 4, then 5. And if I said I move from this level to this level to this level to this level, you can say that I'm moving up, I'm moving upwards. And I use that in quotes, upwards in the W direction, because remember this is the W variable. We're talking about that constant being our W value. And so this is the best way to understand how to move through 4D space, and in some ways how to visualize 4D space. But it's a fairly difficult concept for us to do, again, because we live in a 3D world. But from a computational standpoint, it's not that difficult. We're just adding a third variable in our independent list of variables. And so if I did 5, 6, 7 independent variables, that from a computational standpoint is easy to do. From a visualization standpoint, not so much. But the way we can do it for at least four-dimensional space is to think about these in level surfaces terms. Okay, similar to what we did with level curves for 3D space.